Alrighty, here we are in chapter 3.1. We are in a new chapter here, and this begins with the exponential function. So it's a new function for a lot of us here. Our next one that we're probably talking about after this one would be the logarithmic functions. Alrighty, so exponential functions on tab at first. So what do we have as its objectives? We're going to evaluate exponential functions. We're going to graph exponential functions. We're going to evaluate functions with base e. And then we're going to use compound interval formulas. Okay, so let's begin with the definition of what an exponential function is. An exponential function f has base b is defined by f of x equals b to the x or y equals b to the x, where b is a positive constant other than 1. B has got to be greater than 0 or not equal to 1, in other words. And x is any real number. Okay, b is called the base. Okay, and like I said, it could be any number greater than 0, but as long as it's not equal to 1. So we're going to look at an example of evaluating an exponential function. Okay, the exponential function f of x equals 42.2 times 1.56, I think, yep, to the x power. So in this case, your b is 1.56, and you got a constant out front. Models the average amount spent f of x in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours of shopping at the shopping mall? So that formula models, in other words, what they're basically saying is if you want to know how much money is typically spent at a shopping mall, plug in the number of hours you've been at the mall in for the x. In this case, they want to know what it would be at 3 hours. So we substitute 3 in for the x and evaluate the function. So you don't need a calculator. So 42.2 times 1.56 to the third power, because we're putting 3 in for the x, and it turns out to be 160.20 followed by some other decimals like 676. And so it's approximately $160. So after 3 hours at the shopping mall, the average amount spent will be $160. Okay, so what would it be if you spent 4 hours? Well, what's going to happen is, since it's going to be 4 hours, it's going to be a number greater than 160 because the base is greater than 1. Okay, the bottom line here is, if your significant other goes to the mall, you want to minimize the number of hours that they stay at the mall if you're trying to save money. Because the more hours you stay there, the more likely you're going to spend money. That's kind of what they're basically saying to you here as far as this. So if you spend 2 hours, you're going to be spending less than $160. So, but anyway, this is an example of what an exponential function is. Basically, it starts out kind of low, and then at 2, at 3 hours, 4 hours, and then it just kind of starts skyrocketing upward. And that's kind of the idea of what an exponential function looks like. But let's look at it a little bit more. Let's look at what it is looking at the graph. So graph of an exponential function, f of x equals 3 to the x. So we set up a table of coordinates that plot the points, connecting them with a smooth continuous curve. So we're going to start at -2. We're going to put -2 in. 3 to the -2 is 1/9. You put in -1, it's going to be 3 to the -1, which is 1/3. You put in 0, 3 to the 0 is 1, remember? And you put in 1, 3 to the first, of course, is 3. So if you plot those 4 points, you plotted -2, 1/9, you plotted -1, 1/3, you plotted 0, 1, and you plotted 1, 3. So notice as you go from left to right, how the graph actually starts increasing, and it starts increasing pretty fast. But on the left side, it kind of levels off. Okay, so that's what happens. That's what exponential functions do. One end will level off, the other end will shoot off to either infinity or negative infinity, depending on what the value of the leading coefficient is. Okay, and it also depends on what the base is. But the thing is, it levels off on one side, okay, and runs off to oblivion on the other side. Okay, so that's how you kind of recognize what an exponential function graph looks like. So if you see any graph that does that, most likely it's going to be an exponential function. One end levels off, the other one runs off to oblivion. So they kind of look like this one right here, like a backwards L shape. Sometimes they'll look like a forward L shape. Sometimes they'll look like a 7, because when you have one of the graph levels off one end and it goes down, it kind of looks like a 7. And the other possibility is it levels off the right side and runs off to negative infinity. That would be like a backwards 7 shape. But this was what I would call a backwards L shape. But that's kind of what they do. They level off at one extreme, and at the other extreme they run off to oblivion. It could be a positive or negative infinity, making that shape I just referred to. So, okay. So example, transformations involving exponential functions. So use the graph of f of x equals 3 to the x, when we just did, to obtain the graph of g of x equals 3 to the x minus 1. So we begin with graphing 3 to the x, which is what we just did a while ago. So we identified 3 points in the asymptote. So if you look at that, it levels off to the left side. So it gets closer and closer to the x-axis to the left. So there is a horizontal asymptote at y equals 0. So at y equals 0 there's a horizontal asymptote. Now what we're going to do is we're going to shift it 1 unit to the right. Why is that? Because we remembered in transformations back in the previous section, when you have an x minus 1, that is a horizontal shift to the right. We learned that in transformations. So you take the x coordinates on each one of those points in that picture and add 1 to them. And the result is the red graph that you're seeing here. So the black graph is still in this same position. So at 1, 3 will change to 2, 3. 0, 1 will change to 1, 1. And negative 1, 1/3 will change to 0, 1/3. Okay? And then, so it's the same shape. It's just been shifted to the right. So that is still an exponential function. It's just an exponential function that's been transformed to another new location on the coordinate plane. Characteristics of exponential functions of the form f of x equals b to the x to the power of x, or just b to the x power. Okay, so number 1, the domain of f of x equals b to the x consists of all real numbers, negative infinity to infinity. The range of b to the x consists of all positive real numbers, 0 to infinity. So unless you've transformed it, if you look at that one of those original pictures, okay, it goes from negative infinity to infinity. There's no vertical asymptotes, in other words. But the graph, remember, is a horizontal asymptote on the x-axis, and it had that shape L, so it's above the x-axis. So it stayed above the x-axis. So that's why the range is 0 to infinity. That's why it doesn't get a bracket, though. The bracket, because it doesn't include the 0 itself. The graphs of the exponential functions of the form f of x equals b to the x passes through the point 0, 1, because f of 0 equals b to the 0, which is 1. So it's a common characteristic of an exponential function that has not been transformed. Now if you move it around, it's not going to go through 0, 1. Like that red graph we just talked about, the 0, 1 was moved to 1, 1. So that one doesn't go through 0, 1 because we moved it. But if you don't move the object, it's going to go through 0, 1. They all do, unless you transformed it. So therefore the y-intercept is 1. That is a key point. Okay? There is no x-intercept, because remember there's a horizontal asymptote on the x-axis, but it never hit the x-axis. So there's no x-intercept. If b is greater than 1, b to the x has a graph that goes through the right and is increasing function. So it kind of looks like that backwards L shape I just referred to a while ago. And the greater the value of b, the steeper the increase. So 4 to the x is steeper than 3 to the x. It's more sharper corners up. So 3 to the x is kind of more gradual. 4 to the x is a little steeper than that one. And a 5 to the x is even steeper. So it kind of looks more in the shape of an L the bigger the base is. Okay, so 2 to the x is not quite as steep as 3 to the x. So, all right. Next one, if b is between 0 and 1, like 1/2 or 1/3, okay, then f of x equals b to the x has a graph that goes down to the right and decreases the function. And the smaller the value of b, the closer to 0 it is, the steeper the decrease. Okay, so if you have like 1/2 raised to the x power, then that one's going to look like going down, but there's still a horizontal asymptote on the positive x-axis. Okay, so that one's going to look like a forward L. It still goes through 0, 1 though. If you have 1/2 to the 0, you'll still get 1. So the y-intercept is still the same. Okay, if f of x and b dx is 1, it's a 1-to-1 function, and it has an inverse that is a function. Now that one we'll talk about a little bit more when we start talking about logarithmic functions, but you do know at this point about 1-to-1 functions. Remember, they pass the horizontal line test, so therefore since it passes the horizontal line test, it will have an inverse function. What is that inverse function called? You have to wait for it. Okay, the graph of f of x equals b to the x approaches but does not touch the x-axis because it's the horizontal asymptote. And y equals 0 is the horizontal asymptote. Alrighty, so and this is what they look like. This is I always think pictures are worth 1,000 words anyway. So it's the first three can basically be encompassed by the blue graph. Okay, b is greater than 1. Okay, it levels off to the left and it runs off to infinity to the right. And the bigger the number on the b is, like if that graph was 3 to the x, 4 to the x would even be steeper than that one, that blue graph. Okay, now the red graph is when b is between 0 and 1. But notice they both go through 0, 1, right? They both go through the ordered pairs. They both have the same y-intercept, 0, 1. That's where that's a common point, if you will, 0, 1. But if you had 1/2 to the x and compare that to 1/10 to the x, the 1/10 is smaller than 1/2, so therefore it would be even steeper than 1/2 x is. So it would be sharper upward to the left in the second quadrant. So but that's what they do. Now again, these two graphs here is a graph of an exponential function that has not been moved. So you haven't transformed it. You haven't moved it right 1 unit. You haven't moved it left 1 unit. That's just the given exponential function. But I want you to notice the characteristic that's in common to both the blue graph and the red graph, depending on no matter what the b is. They level off at one extreme, and they run off to oblivion, in this case positive infinity, at the other extreme. So the blue graph levels off on the positive x-axis, and on the other side it runs off to positive infinity. The red graph, on the other hand, levels off on the positive x-axis and runs off to oblivion, positive infinity, on the left side. That's what they do. That's what exponential functions do. See, everybody can recognize the graph of a quadratic function. Why? Everybody recognizes the graph of a quadratic function because their shapes are the same. It's a parabola. If it's a parabola, you know it's a quadratic function. Everybody can, if everybody sees a line, okay, then they know what kind of a graph that is, okay, because they know what kind of a function that is. Because a line is what kind of a function? Yeah, it's a linear function. So every line that you see, you know it's a linear function. Every parabola that you see, you know that's a quadratic function. Well, when you see these things, these blue and these red graphs here, when they level off one end and go off to oblivion on the other side, you know it's exponential. Okay? Do you see the connection? You're just adding to the number of functions that you know. Up to this point, you probably only know a few graphs, functions, and what they look like. You know what lines look like, and you know what they are, you know what parabolas are, and you know what they look like. And we're trying to teach you different functions. We've talked about polynomial functions. We've talked about rational functions. This is just another one to put in our tool belt, an exponential function. It's just another addition. So, alrighty. Now, the natural base e. Okay, the number e is defined to be the value of 1 plus 1 over n to the nth power as n gets larger and larger. So as n runs off to infinity, the approximate number of e is out to 9 decimal places is 2.718281827. It's actually 281828. That next number is actually an 8 because it's rounded up. So, but anyway, that's out to several decimal places though. But this number you may or may not recognize. It kind of depends on where, how much math you've had. The only irrational number that you probably know about for sure is pi. Pi is like 3.14159265. So that's pi. That number you recognize as 3.14. And you know that because everybody's required to take geometry in high school. But a class that you're not required to take is classes like statistics, finance, and things like that, when you would use kind of interest rates. But if you had to take those classes, you probably run across that number there before, E. But a lot of people don't take those classes, so this is the first time they've ever seen it. But E is just another irrational number, just like pi is. The origination of them is different. Pi comes from, basically it's a ratio of the circumference divided by the diameter of any circle. That's how you generate pi. But on E, it's generated by this formula here. Okay, but it's still an irrational number, just like pi is an irrational number. And it's, like, why do they call it E? Well, E is because the guy who developed this number or created or who thought of this number was a guy named Leonhard Euler. His last name is spelled, even though you say Euler, it's spelled this way, E-U-L-E-R. What do you think the E comes from? He named it after himself, okay? He named it after the first letter of his name. So E is 2.718. That's the history of where E comes from. It's Leonhard Euler, okay? So we call that irrational number E approximately 2.72. It's called the natural base. The function f of x equals e to the x is called the natural exponential function. Now remember, on an exponential function, it's f of x equals b to the x power, right? As long as b is greater than 0 and not equal to 1, you can make any number the base, as long as it's greater than 0 and not equal to 1. Well, e would fit that description. 2.72 is not equal to 1, and it's greater than 0. But we call that the natural exponential function because e is the natural base. Okay, and this e is used a lot in statistics, calculus, a lot of different areas of mathematics. Okay, so it's just as important as pi is, even though when we're growing up and taking our math classes, we don't hit that number necessarily till later on in your math career. Pi is taught to you much earlier in that. So, but E is called the natural base. All right. So let's look at an example. Evaluating functions with base E. Okay. So the exponential function f of x equals 1,145 e to the what is that? 0.0325x, and it models the gray wolf population of western Great Lakes. F of x, when it's x years after 1978, okay? Project the gray whale's population in the recovery area in the year 2017. Now, you don't put 2017 in for the f of x, do you? Okay, because x, look what it says x is representing. The x is representing the years after 1978. So how many years have passed between 1978 to 2017? Well, you'd subtract 2017 minus 1978 into about 39, maybe? Yep. So because 2017 is 39 years after 1978, we substitute 39 in for the x in that given function. So again, pull out the calculator. And you're like, well, wait a minute, that's e. Is that on my calculator? Yes, it is. Just like 3 is. Pi is on your calculator because it's an irrational, but e is located there as well. Okay? And the question is, how do you access that, find that button on your calculator? Well, most calculators, and everybody's calculator is different, but most of them, if you're using the scientific calculator, is found in it's not on a button itself. It's in the area above a button, which you have to hit your shift or second to access it. But what you do is you search for the LN button. And you're like, what is the LN button? We haven't got there yet. Okay? So find it says LN. It's usually right beside the button that says LOG. and you probably know what that is, but LOG, and then right beside the LOG, there's probably an LN, okay? So if you want to know how to, you remember E is like 2.718, what you could do is hit Shift LN, and what pops up is E with a caret symbol and probably a parentheses. Punch in 1 for right now, and then close that parentheses off and see what it says. You remember that 2.718 number that was on the previous slide? That's going to come up. Okay? So that 1 is its exponent. So e to the first is at 2.71. So you might want to do that before you actually even do this problem. Just see if you can actually do that on your own calculator. So let's go over that again. You hit Shift LN, and then E caret symbol pops up with a parentheses probably, and then punch in 1. Close that parentheses up because you always have to close a parentheses that you opened up, and it opens up a parentheses automatically. And then hit enter, and if 2.71828, you're ready to go with it. Okay, that's how you do it. But on this one, you have to punch in 1145 first. You don't have to hit the multiplication, but hit 1145 and then hit Shift LN, and then hit that E with a caret symbol pops up, and left parentheses. And then punch in the what was it again? 0.0325 times 39, and close that parentheses off. So in between those two sets of parentheses, you should be providing 0.0325, and then hit a multiplication, 39, close that parentheses off. So it makes the calculator carry out the multiplication of the exponent first. Then it takes e to that power, and then it multiplies it by the leading coefficient, 1145. The good news is these calculators these days are really nice that they'll do all that for you. Back in my day, that wasn't the case. We had to do a certain order, and if you didn't follow the right order, then you messed the answer up, okay? This time, these calculators, you can punch it in. It's kind of like you see it on your paper, and it does the order of operations already for you, which is pretty nice. But anyway, after you do that, you put the 39 in, you'll get 4,067. Now, it's not going to be exact, but that's why it says approximately 4,067. And remember what you're trying to do. You're projecting the gray wolf's population in the recovery area in 2017. So in 2017, they can expect, or they expected anyway, because it was 2017, they expected 4,067 wolves. Okay. Now you're like, well, how many wolves were there to begin with? Well, you could put 0 in for the time, and I think if you carry that time out, you'll get 1145 times e to the 0, because those two multiplications will be 0, and then e to the 0, remember, is 1, and then 1 times 1145. You could do this on your calculator as well, but if you do all that on your calculator, either way, you would get 1,145 wolves. So in 1978, they counted the wolves, and it was 1,145. In the year 2017, in this recovery area, they can expect 4,067. I want you to understand, is that the case? If they go back in 2017, will they count that many? Will number of wolves be that exact number? Could be. You got to remember, these are models. Sometimes modeling doesn't represent real life. Okay, these are estimations modeling. Okay, that's what's called a model. Okay, they're not saying what they're doing is exact science. Okay, don't take it that way. So when I look at these kind of models like this, and when I get that 4,067, I would say, they're probably going to be about 4,000 to 4,200 4,000 to 4,200 wolves in this area during that time. I kind of underestimated and overestimated at the same time, and give me a range. Okay, so I look at their result by their model. The model is not, like I said, exact science. Okay, so you got to look at the big picture. Don't take things so literal when they do that. But that's the idea. So this indicates that the gray wolf population in the Western Great Lakes in the year 2017 is projected. That's the key word, projected to be approximately 4,067 wolves. All righty. Formulas for compound interest. All righty. After T years, the balance A in an account with principal P is of annual interest rate, R is a decimal form, is given by the following formulas. For n compounding periods per year, A equals P times 1 plus R over N raised to the NT power. Okay, this is a good time to stop and write these formulas down, because that formula will not be provided to you. You need to know it. So this is compounded n times per year. The next one, for continuous compounded, A equals P times e to the RT power. P is the principal, the R is the rate as a decimal, and T is the time. The n on the first one represents the number of times it's compounded per year. So if they say it's being compounded monthly, n would be 12. If they say n is compounded semi-annually, n would be 2. If they say it's compounded quarterly, n would be 4. If it says it's compounded weekly, n would be 52, because it's 52 weeks in a year. Okay? So you got to look at it that way. All righty? Then for continuous compounded, notice the E there, that natural base is there. So A equals P times e to the RT power. So these are two types of compounding. And to be quite honest with you guys, they're very close in the amounts that you get. If you use one versus the other, the continuous is a little bit more than the compounded periods per year on the number one, but not by much. Okay? So the compounding periods per year on number one, what that is doing basically is there's a finite number of times it's being compounded. So if it's compounded monthly, you have to wait 30 days before it's compounded again. If you compound it, if you compound it weekly, then you got to wait 7 days before you can compound it again. Whereas the bottom one is continually being compounded, which you think would be a great advantage. And it is an advantage, but it's not a great advantage. Okay? The R is the key, the thing that tells you how much money you're going to get as a key. Higher the interest rate, R, the better off you're going to be. The R is the key as far as how much you're going to make in the account. Okay? Whether it's compounded 12 times or compounded continuously. Okay? That does make a small difference. But the biggest difference maker is the rate itself. Alrighty. So let's look at an example using compound interest formulas. Alrighty. So a sum of $10,000 is invested in an annual rate of 8%. Find the balance in the account after 5 years subject to quarterly compounding. So remember, n is 4. So we will use the formula for n compounding periods per year, which makes it n equals 4. So we just plug everything into the formula. So it's $10,000 was put into the account. 1 plus 0.08 divided by 4, because it's 8%, and you got to write them as a decimal. Divided by 4, because it's n is 4 times a year. And 4 times 5. Why 5? Because it says after 5 years. So put those numbers into the formula, into your calculator correctly. And by the way, I would change the exponent to 20, because 4 times 5 is 20. You don't have to do everything the hard way. You can just make that a 20 when you plug it into a calculator. So it's $14,859.47 rounded to the nearest cent. So that's how much money you would have in the account at the end of 5 years if you compounded quarterly. Now understand, banks always round down. So even if it was 0.478, it would be most likely 47 cents, even though you'd technically round it up. I think my math lab would round it to the nearest penny. So they would say if the next number after the 7 was 5 or higher, they'd probably go up. But in reality, they always round it down. Banks want to save the pennies when they can. So they'll make the argument, well, it didn't quite make it to that next cent, so you didn't get it. So that's kind of the argument that they would use. Alrighty. So the balance in the account after 5 years, subject to quarterly compounded, will be $14,859.47. So let's use this one. A sum of $10,000 is invested at an annual rate of 8%. Find the balance after 5 years, subject to the continuous compounding. But you're like, well, that looks awful familiar. Look at that problem. That was $10,000, 8%, compounded 5 years on a quarterly basis. Here, it's the same numbers, like $10,000, 8%, and 5 years, but it's compounded continuously. So let's look at this one. We will use the formula for continuous compounded. So A equals P times E raised to the RT power. By the way, I have a pet name for that one. I call it the shampoo formula because of the PERT, P-E-R-T, and basically it's a shampoo. And I call that this is my little name for it. I call it the shampoo formula. So A equals P times E raised to the RT power. So you put your $10,000 in for the principal, E, and the rate is 0.08 because it's got to be written as a decimal, and time is 5. You do the math, it's $14,918.25. So that's how much money you're going to have after 5 years compounding it continuously. Now let's go back to that previous slide again. Let's look at that again. It was $14,859.47. That's for that one. And then back over here, it's $14,918. So it's about a $60 or so difference between those two. It's not a great amount. It's not a great amount, but it is more. So the balance in the account after 5 years, subject to the continuous compounding, will be $14,918.25. Now, guys, we're going to encounter these things again later on when we talk about another type of a function. Okay, you're introduced to these formulas now, but you'll see them again a little later. Okay, so this is not the only time you're going to see these formulas. So you'll get more accustomed to them as we progress through this chapter. So, but right now, okay, you got to know those formulas, okay, and basically right now it's what I call plug and chug, okay. Get the information that you're giving me, put the numbers into the formula, and get the answer. At this point, that's all it really is involved. A little later, it becomes a lot more complicated to get the solutions to these applications, okay. So what I'm telling you is the word problems get a little bit more complicated a little later, okay. But so you need to know those two formulas. Now you got to remember how exponential functions work, okay? So that's the idea, and how to use your calculator. So 3.1 is not so bad, but we do get a little more complicated as we progress through chapter 3, okay? So again, but it's a good idea to go back to these slides one at a time, pause the video, and just kind of write them down on your paper. It just sticks a little better when you do that. So I know you're getting tired of me saying it, but I'm going to say it forever. So, okay. So this is this one. This is complete. If you have any questions on it, you want to see another problem or two, a couple more graphs on these exponential functions, feel free to contact me, and I'll send you another example of this one. But in the meantime, I'll see you at the next video in our next section. Have a good day.